Hi everyone. If you like the way I teach and want me to be your teacher, the link to my engineering fundamental school is in the description below. Enjoy the video. In the last couple of videos, we've been really focused on the idea of finding moments of areas, either the first or second moment of areas. We said that that first moment of area could be applied to the finding centroids of a body, and the second was the moment of inertia. And we use calculus, we use tables to find those centroids and those moment of inertia. And those ideas were dependent on your understanding of statically equivalent systems. And if you want to understand that intuitively, I made a video about it that you can review. Today, we're going to look at the centroid of a line, which is given by this equation. L is the total arc length, and dl is the differential length of a line segment. We're going to go ahead and do an example here, which is more of an exercise in calculus on how we parameterize a curve, and then we go ahead and are able to find the length and the centroid. If we wanted to parameterize this curve, we can set x equal to t, and following the yx relation, we know that y would be equal to t plus 1. Now we have a position function where if we're given a t, we'll be able to trace out the curve shown on screen. For instance, at time equal to 0, we're at 0, 1. At time equal to 1, we're at 1, 2. This position vector is tracing out the path shown here, and the position can have a speed. The speed is just the time rate of change of the position. Technically, it will be called the velocity, right? Velocity is a vector and speed is its magnitude. So if we take the time rate of change of this position, what we're going to get is 1, 1. And if we wanted to find the total length, what we could think about is this scalar relation. The time rate of change of the position is equal to the speed. What does dr really represent? Dr is a small position vector. It's the length of a small position vector. If we add up all those little lengths, what we're going to get is the total arc length. If we go ahead and compute this integration, right, we solve for that dr, we move the dt to the other side and perform the integration from x is 0 to 1, which means t is also 0 to 1. We can take out the speed or the magnitude of the velocity, which is root 2, perform the integration, and get the arc length is equal to the square root of 2. This makes sense. If we draw a triangle with side lengths of 1 and 1, of course we'll get the length is root 2. Now if we're trying to find the y-coordinate of the centroid of this line, we can isolate using that relationship shown on the left side of the screen. What is y? Y is t plus 1. dl can be described by v dt. dl is just dr. And the length of that line is the square root of 2, like we found before. We can go ahead and perform this integration. You can see that root 2 can be taken out, and after we integrate, we get 3 over 2, which kind of makes sense. It's 1.5. You would kind of expect the y bar coordinate of that line to be right in the middle. Same thing with the x bar coordinate. If we go ahead and integrate, what we get is that the x bar coordinate is equal to 1/2, which really makes sense. It's right there in the middle. The midpoint of that line is that line's centroid. Let's draw a schematic here where we draw the position vector r at some time t, r at some time t plus a delta t, and their difference is going to be a delta r. As that delta t shrinks to 0, the delta r will become a dr. And of course, the sum of all those little drs is what we call the arc length. Okay. If we have an arbitrary function in a Cartesian plane, and we write down the relationship between the centroid of that line and its arc length, shown here, what if we multiply both sides by 2 pi? We get a left side term and a right side term. Let's think a little bit about what the terms under the integral mean. We have a 2 pi y term. That is a circumference, right? The circumference of a circle is 2 pi r. So this would be a circumference of a ring. What about the dl term? That will be the length of a small position vector. If we take a circumference and multiply it by a height, what we're getting is a surface area, right? The radius of that would be y. The circumference is 2 pi y and its height would be dl. That's a surface area. If we add up all those little surface areas, we get a total surface area, and that can be computed here with this relation. This is called the first theorem of Pappus and Guldinus. The second theorem is related to areas. Again, we multiply the relationship between the first moment of area by 2 pi on both sides. And what do we kind of get here? We have a 2 pi y term. That's the same circumference we had before. It could also be called the height, and this is an area. What's an area times a length? It's kind of like a rectangular prism, except we kind of curl it into a ring. If we sum up all these volumes or all these rings, what we'll be able to get is the total volume. This is called the second theorem of Pappus and Guldinus. So this is one of the applications of finding centroids, and it's used to find volumes and areas of surfaces of revolution. One popular surface of revolution is a can of soda. So right now we're going to be using the theorem of Pappus and Guldinus in order to find the volume and surface area of a Coca-Cola can. We're given all of the dimensions. We have the length of that inner lid, the outer lid, and its two heights. And we could kind of project it, right, as a just shown in the right half of the plane, right half of the Cartesian plane. Why would we want to do this? Because this is what we rotate around in order to achieve a full Coca-Cola bottle or a full Coca-Cola can. Let's go ahead and define these dimensions. Since their diameter is on the left, I want them to just be radiuses on the right, and the heights will stay the same. How could we go ahead and compute the surface area? We think about the first theorem of Pappus and Guldinus. 2 pi x bar times L is equal to the surface area. All we're going to do is go around each line and find 2 pi x bar times L. We're going to add them all up and we'll be able to get the total surface area. We know 2 pi is going to be constant for each term. So for instance, the first line, it has a distance, right? I just drew that dot denoting the first area, second, third, and fourth area. Let me go ahead and write these out. For the first area, what we have is 2.1 over 2, which is the centroid location of that line, multiplied by the length of the line, which is 2.1. For the second length, what we have is 3.1, which is the length all the way to the end of the can. We have to subtract off half the length of the x length of this chamfer. What's the x length of this chamfer? 3.1 minus 2.1 is just 1. So half the length would not be 1/3, it will be 1/2. And its length is going to be, we can use the Pythagorean theorem, it's root 2. The next one, the third area, is going to be 3.1, which is the distance all the way to the end. That's the x-coordinate of the third little line, multiplied by its length, which is 11.2. And what about the fourth area? 3.1 over 2, multiplied by its length, 3.1. If we go ahead and perform this calculation, we get that the surface area is approximately 286 square centimeters. How would we go about finding the volume? we'll write the second theorem of Pappus and Guldinus on screen. All we need to do is think about what kind of areas we can split that shape into. And what I'm thinking is that we can split it into the overall rectangle and just subtract off the little triangle that's missing on the top right. The overall rectangle would be 3.1 multiplied by 12.2. We would take that area and multiply by its centroid, which is 3.1 over 2. That would be if we wanted to find just the area, just the volume of the cylinder. Now, what about the volume that we have to subtract off of that upper right triangle? Well, that'll just be the distance to the centroid, which is 3.1 minus 1/3, right? We have to remember the third of the base is equal to the coordinate of that centroid, right? And the base is 1, but it's not measured from the left to the right. It's actually measured from the right to the left. So orientation is really important when you're looking at centroids. 3.1 minus 1/3. If we know that distance, all we need to do is calculate the area of the triangle. Its base and height are 1. We have to divide by 2. Base times height over 2 is the area of a triangle. If we perform this computation, what we get is that the volume of this can is equal to around 360 milliliters. If this video was helpful for you, please like and subscribe, as it helps me out a lot. Keep learning and keep working hard. Goodbye.